I think so. I'm not like I want to dig a little bit deeper into these, right? Because I have the feeling, like for me, it's not obvious that these kind of the reason why you can do the differentiation, like the derivation part of things, like it's just because of the symmetry. I can't, it's hard to believe that like that applies to any kind of circuit, right? So I wanted to, man, I wanted to kind of play with maybe go back to just go back for a second to like the you know the one where I have the circuit, so it's these, it just has one qubit, right? And let me see, what am I doing? So the circuit is okay, so it just depends these, and it just depends measure, and it just has 2 qubits, but I want this to just have 1 qubit. Um, and this is looking, yeah, I think ChromaChem is working well now. Cool. So I just want to first of all try to think. So I want to try basically a sort of a more complex circuit, but still just with one parameter, and then I want to really try to figure out the two parameters thing. And if we have time, I really wanna go into a paper about optimization that I was recommended, you know, by. See if I can take the paper from here. Just didn't want to show. Just don't want to show some of the prior messages here. Exactly. The So this is from. I'll show you guys in a second. This is from Gerard McLean, if hopefully I'm pronouncing his name correctly. Um, and it's this paper. Why does this show so big? Give me a second. Okay, so there you go. So this is the paper, Low Depth Mechanisms for Quantum Optimization. And I wanted to kind of sort of at least do a first, because it's a long paper, so it's 30 pages. I won't be able to cover everything. Um, but I see here there's a bit of a, there's again like sort of the minus in here. I want to kind of dive into this and see if there's more subtleties interesting to explore in terms of the optimization. How can you optimize quantum circuits? Um, I think it can just be it can be fun. Um, but let's first try to do these for a second. So I wanted to kind of what I wanted to do is I wanted to do two things. So I wanted to make the circuit a bit more complicated. What about we let's indeed have 2 qubits. So let's indeed have 2 qubits, but let's say, for example, let's append circuit documentation. So I'll have to, I'm just a noob in all these. So control not. Circuits, gates. How do you do this? Circ. Okay, and then you give it the qubits. Can you? But you really have to create the qubits like these. Have I created the qubits like these? Qubits, yeah. So I can just say circ. Was it CZ? Okay, so I guess CX. So first we have rotation layers. So maybe I can do a CZ actually, and then qubits. Well, Z. Come on, what am I doing? Ah, now qubit 0, qubits 1. So if I do these, circ is not defined. What is not? What is what? Sorry. I gotta do the whole thing again. And I want to run these. And so, it's still running. Okay, cool. I want to see what happens now with the control set. See if the circuit changes a lot. Okay. Length is not defined. Where is length being used? Oh. That's length, I guess. And I guess that's where it goes. It's not a circuit, but it's... Oh, I gotta probably just append it. Oh yeah, append and then just like these. Okay, cool. So, yeah, it's so easy to forget this stuff. I have such bad memory for these. Append and then we'll just do a CZ on qubits. There you go. And I will probably have to do circ CZ. There you go. Okay, so there's... Ooh, interesting. Yeah, but I don't want alpha there. Give me a second. So I don't want... You know, for each qubit, I just one. Let's say... Let's cheat. Okay. So the expectation value doesn't change. Let's see. Actually, let's open up. Let's open up Quirk in here and play with these a little bit. So if we have a Y rotation, right, we can even just have like something like these. And then we have like a control Z. Well, yeah, that obviously doesn't change anything. Let's do a control X, okay? See what happens. Okay. Not much in terms of expectation value. Oh yeah, but I don't know how to calculate the expectation value for multi-qubits. I think that's the problem. Because I'm doing the expectation value for, what am I doing? I'm just taking the results. Multi-qubit. Or isn't there just a way to calculate the expectation value circ? Expectation value with circ. Isn't there just a built-in way to do that? I think there should be a way to say expectation value of the Z operator, something like these. Oh, it's deprecated, we'll remove expectation from state vector instead. Okay. So what is these? So what is these? Circ X and expectation. So, okay, wait a second. So, evaluate the expectation of this Pauli string given a state vector. So you have a state vector. Okay, so and then this is the expectation value of this operator applied to qubit 0. Okay. Compute expectation value of this Pauli string with respect to a state vector. By convention, expectation values are defined for Hermitian operators, and so this method will fail if the Pauli string is non-Hermitian. State must be an array representing a state vector. Qubit map must assign an integer index to each qubit in this Pauli string that determines which bit position of a computational basis state that qubit corresponds to. For example, if state represents these, then uh, mm, I don't get it. Isn't that a mistake? Shouldn't this be Q1? Mm, then qubit map. So an integer index to each qubit in this Pauli string that determines which bit position of a computational basis that qubit corresponds to. Something's off with these though. So the expectation value in this, okay, so the expectation value in this case is 0 because basically we've done a NOT gate on Q0. Hmm. I'm not sure I understand that this is the result is the expectation value. But why it returns 0? It returns 0. Okay, let's try to use this though. Um, mm, let's try to use this. So if how do I get the state? So circ state vector. How do I get a sample state vector? So instead of getting the measurement results, I wanna get the state vector. Sample state vector. Samples repeatedly from measurements in the computational basis. No, that's not one. I want state vector. I want to get the state vector. Product state. I want final state vector. So can I just the circuit, gate operation, or tree of operations apply to the initial state? Okay, this is all optional. So can I just final state vector? Okay, param resolver, qubit order, parameters to run with the program. So if I do instead of simulator run sweep, so what I can do is I have oh great, circ final state vector, and I give it the circuit, and let's just I just want to play with this for a second. Let's not append this, let's just append a control NOT gate, print the circuit, and then print the state vector. And let's not plot anything. Final state vector. Circ final state vector. API reference Y. That's not the way it works, or what? The program is the circuit. It tells me, oh, maybe I just have an old version of Circ. How do I upgrade Circ? Installing Circ. Installing in Windows. Can I just run these? Python. Would this update it actually? I'm just using the wrong version, that's it. Right? The wrong version, like an older version. Whatever. Access denied, permissions. Come on. Whatever, I'll have to just use the... what is the version I'm on? I'll just have to use the old way. Expectation from state vector, no, circ. I should install these. I should install these. Give me a second. What do I want to know? What do I want to do? I want to check. How the hell do I just do like a... I hate these. I'm just basically checking how do I get, because I'm like on a today I'm recording on a shared computer, and I should have just like used so I might just have to use... Let me pause for a second and see if I can just fix that, because I need to check out some passwords. Whatever, I think I can't figure out how to update that, so I'll just do it old school. So I'm trying to figure out how to calculate the expectation value by hand, as in like averaging the staff, the way that I'm doing it here. So I have like these, and I get the results, and then if I print the values, if I print the result, what I get is like oh yeah, 0 all the time. I mean, that's, yeah, I guess that's kind of fine. Let's just go back to these. Actually, let's see. Yeah, so okay, so you get like 0 and 3 and blah blah blah. So you kind of get like these, you know, these elements. So, but I was not sure, like in here, I'm like, you know, I'm basically saying, okay, so what's these times -1? Because I knew the 0 and 1, like the eigenvalues would be like -1 and 1. But like I'm not so sure how you do that with multiple qubits. So that is returning 1 if the qubit is in the state 1 and 0 if the qubit is measured as 0. However, it's relatively easy to perform a change of basis unitary to our quantum circuit just prior to measurement. Eigenbasis, planetary operator. We measure the state and the computational basis and execute the job to get the counts and probabilities. And using the previously computed eigenvalues of A, we can now reconstruct the expectation value. So we need the eigenvalues of A. So we have the shots. Okay, so you need to compute the eigendecomposition of our Hermitian observable, but this is just like the the ZZ. So okay, so I think it's gonna be a combination of -1s and 1s. Like I don't know if it's just a multiplication. You know what I mean? I think this is something um, like the result. So I think that it's something like these. So for 2 it's like 1 0, so it's basically -1. And for 3 it's like 1 1, so it's like +1. I think that's the way. I think that's the way. If I would do it like these, then I would have that the expectation value so sorry, I don't want to print these. Say if my circuit has like, for example, if we're not let's just do something stupid for a second. I just wanted to, so let's say it doesn't do this. It does a circuit append exponent half turns. So it does like a, for example, I don't know, circ like a Z gate, which is not going to do anything. Oh, but I cannot build it like this. It will be easier. It will be easier if I just do like, if I just do like that, Z layer, and then there's like a Z layer, and that's what I basically do. If I do these, I'm just gonna create like a, yeah. Okay, so that kind of makes sense. If all what I, because it's basically 0. If it's if I do like, if for example you know, like apply, for example, circuit append. I think that's the correct way to do that. Circ Hadamard, and then I just do these. So now I applied Hadamards. So what? What is wrong here? What have I done wrong? Qubit 0, qubit 1. Wrong number of qubits. Length is 2. Why is wrong number of qubits? Oh, sorry, because the operation just has like, I think it just takes one parameter, so I cannot, so I have to do it like this. Oh, that doesn't look good though. So that's definitely not what I expected. So this must be wrong actually. Eigenvalues of Pauli Z the qubits. What are the eigenvalues? Pauli matrices. Or how do I calculate the eigenvalues? Come on, that's simple stuff. The eigendecomposition of parameter estimating was analysis in the eigenbases. To see why not these. Or simply measure the computational basis. So what is he here doing? So it's getting the shots, it's getting the counts, and then it's getting the probabilities of each, and then the expectation is lambda at p. What is these though? What? The doc string for that function is z. Yeah, that's what I just that's what I want to know. ZZ operator. Oh, come on, just how to calculate eigenvalues using NumPy. There you go. And so if the eigenvalue is A, so A is just the matrix, I guess. The matrices for which eigenvalues and right eigenvectors will be computed. So if I just do like let's just do another cell here. Insert cell below. So if I just do for example, the matrix. So the Z matrix is basically NP array of like 1 0 0 1 right? And so basically the tensor product, NumPy tensor product, tensor dot. So if I do tensor dot z, z, and then I print in z, what do I get? Tensor dot 2. That's not what I want. Not dot, but like so it's just z times z. That's it. No, tensor product. Kronecker product. Kron. Cool. Z, Z. Okay, there you go. And now I can say what do I get? NP. Yeah, that's the easy way to do. What? Eigen values of matrix. Oh, did I get these right? Sorry. I think that's I think that's like these, but still, oh yeah, 1 minus 1 minus 1 1. I think this is the idea. So that's so that was right. 1. Okay, no. So 1 minus 1 minus 1 1. So that will be 1 minus 1 minus 1 1. Okay, so and if I'm doing these, it still doesn't make sense. Does it make sense? This should, by the way, these shouldn't vary so much. It shouldn't vary at all. If I just don't have the, that's just wrong. Is it gonna complain? Why do I get all these? So so for each measurement, right, like print R, so I'm getting these counts. I guess it's got some noise. 0 1 2 3 0 1 2 3. Am I doing the right calculation? It's the average, but it's the average. Like, it should be the eigenvalue. That's what we're trying to. Right, because it's 34 twos, 25 zeros. Eigenvals. Okay, so let's try these. That's 1 minus 1 minus 1 1. That's what we have here. Because I was expecting the so there's definitely some noise in here. I think that's I don't know. Is it okay? Is it not okay? I'm really confused right now. If I don't add the Hadamards, right? So it's just an empty circuit. I get like just these. So that's like 1 all the time because this, yeah. So if I mean, that seems to make sense. If I add like, it seems to match. If I add the, if I append like, if I'm just, creating the actual eigen, like the eigen states, right? If I append an x here only, or an x here and an x there, I'm getting also 1. But if I'm appending like, just these, right? Then I'm getting a -1. Yeah, it makes sense. And here I'm getting a -1 as well. Makes sense. Am I? Yeah, -1. Okay. Fine. Yeah. So that seems to be actually fine. Now, if I... So this is sort of the manual one, right? So just the eigenvalues. If I want to now... So what I was trying to do. So I was trying to do basically, I have these with the rotation layer, right? So I have this circuit and the second qubit is always going to be 0. So that kind of gives me the same shape, right? Because I'm only going to get zeros or twos. Zeros or twos. Ones or -1s, right? Yeah. So that makes sense. That makes sense. But like as soon as I complicate the whole thing, like, I mean, what if I just add like the Hadamard here, right? No, not an X, sorry. Like Hadamard. That's like, that doesn't become differentiable. Like how can you apply the same phase shifting rule here? That's what's confusing me a lot. That's what's confusing me a lot, because like how am I supposed to find the minimum in here? If I apply these here, then you kind of see, like, as long as you see, as long as you stay with 1 qubit, you get that thing in there, because then that's the only thing you're shifting. But as long as you add more qubits to the game, that's what's really confusing. Why does the parameter shift rule apply? Like, why can these apply? Maybe, I don't know, maybe this is something that I should just dive into. Like, I'm not even gonna, like, I'm just curious, can I sweep across multiple parameters? Just like to have a 3D version of these. But like as soon as you complicate the thing, it just doesn't seemed like you could use the parameter sheaf rule. Because it's a new combination of all the quantum functions. Importantly, these are quantum functions typically use the same circuit, differing only in a shift to the argument. Okay, unless what you're doing is you're only varying one argument at a time. Of course. But it's not like, no, that doesn't make any sense. Like, look at these. I mean, just look at these, right? Like, if I add this Hadamard gate there in the QB1, then like, don't tell me I can apply the parameter sheaf rule here, because like, single parameterized gate, multiple parameterized gates. So let's read these. Let's see, single parameter is associated with you. Let's remove all the gates. So basically, they mathematically just come down to these multiple The key insight is that we can, in many cases of interest, express this gradient as a linear combination of the same transformation M, but with different parameters, namely. Yeah, okay, but they just actually skipped the actual reasoning. While this construction bears some resemblance to the numerical finite difference method for computing derivatives, here S is finite rather than infinitesimal. Pauli gate example. Okay, so maybe the trick is this pi divided by 2. The trick is that there is some regularity in here. Let's see if we, for example, do like 1,000 or 10,000 dots. Like, it's just too much, probably. Too much. Should have stayed at 1,000. 1,000 steps. Should have stayed at 1,000 steps, definitely. Because maybe it depends on the observable, right? Here we have like a ZZ observable, and so, yeah, I guess it's too much. Same size. So what about like 1,000? Does this still work? What's the problem? X and Y must be the same size. Inputs and values. Oh, sorry. Yeah. Okay, there is, but there is some like, I don't know if there's a pattern here, to be honest. Oh, wow. Maybe we just stretch that like to 10 times pi. Oh, sorry. 10 times pi. I should do it this way. And go back to like 100. Hmm. Yeah. It's like, I don't know. What if I try it with like an X rotation? Doesn't look better. Can I draw a line like scatter plot with line? NumPy. That's the right answer. Which is pretty much the same as plot dates values. Just like these. Okay. Does it show a line? No. Mm. Scatter and show line graph. For red lines and points. What? So I'm not so sure. This is something I can easily get. I don't know. Whatever. Oh, sorry. It's a plot. Okay. So it's not a scatter. It's like a plot. Okay. Yeah. Hmm. Can I make this bigger? Matplotlib plot size. Input figure. Tells you the call signature. Subplot adjust. Plot figure fixed size. Cannot be that complicated. But I gotta import fixed size. Do I? No, just like these. Okay. What is this? Oh, it's just like that. So if I just do okay, if I do like 100 by 100, this is like too big. Probably. Oh, not that big. 30 by 30. It's too big as well. 10 by 10. Okay, so these You could say there's a pattern, but then it's like you gotta find what the yeah, I don't know. What if I just apply like, for example, a let's make it look like these. Okay, to some extent, I can't believe there is a bit of a pattern there, where if you just a bit of symmetry somehow. So it's just not really smooth in this case. So it's going to be difficult, but I guess that depends on really each circuit and whatnot. So it really, yeah, I think it really boils down to these. Now, how can I sweep circling space? Pattern tuples. Key beta, key gamma, permatrace and the ansatz. Can I have like a oh, just like that. I get it. Okay, I get it. I can just multiply the sweeps, and that gives me all the possible combinations, probably. So what I want to do is I want to do something like this. Okay, so let's say let's go. Let's say we have like beta as well. So we have a rotation layer. What does these do? A rotation layer, and then we're going to have another rotation layer right after these on beta. But this is going to be like an X layer, for example, right? So, or a Z layer. And so what is it gonna do? It's basically gonna, why can I copy stuff? Just, oh my god, copy Z layer, and it's gonna add a Z gate, and this is gonna add a Y gate, and we're gonna call it the Y layer, and so this is gonna be called the Y layer, Z layer, and beta, and let's just not have anything else first of all. And now let's try to understand how to do these. So I would do so I would just do it like that, and then it's kind of, the same here, and basically the inputs would just be also a multiplication, I think. Let's keep like a 2 pi here. So I have this multiplication. Cool. And that should basically work. Oh, actually I just made a mistake. I wanted this to be really in for all the qubits, so I really want this length to be there. So I really have to, no, that's correct. Length is there, length is there. Oh, there you go. There you go. But it's still running. Yeah, probably it's too many. But have shapes 100 per 10,000. So that probably doesn't really give me the keys. Can I get the sweep keys? Sweep keys. Circ. I think I just get the keys. Okay, so I can just get the keys. So I should be able to just say inputs sweep keys print inputs. I just want to know what they look like, and we'll just do like, okay, it doesn't take so long. Alpha, beta. No, that's not what I wanted. I wanted to get the I wanted to plot the actual sweep results. Param tuples. Key to value. This is what? This is probably what we want. Yeah, of course it doesn't work. So let me just let's just not run the sweep. Isn't there a way to with the multi-comments or whatever? So let's not just run the sweep. Let's just say param tuples and print inputs. Okay, it's just an iterable. So actually what I should do is for input in inputs, print input is this. And that's a keyword, so I just should call it non-iterable. But it should be iterable. It says here it's iterable. Oh, I should call it as a method. Okay, alpha, beta, alpha, beta, alpha, beta, alpha, beta. Okay, so that's 3. Yeah, of course, that's like 3D right now, basically. So that's for all the alphas and the betas and stuff like that. Okay, so I need to actually construct, like, I need to basically construct the. So how would I do these? So I would basically. Where am I? I am here. So can I just, isn't there like a way for me to just get these lead space? Like what are the methods? Parent tuples and trade over key values. Okay. Keys. So the only really thing that I can do is I can say, so alphas, and that's an empty NP array, and then betas, an empty NP array. And so what I'm doing here is I'm just basically saying alphas equal NP append alphas alpha, something like these, right? And then betas is basically these. And if I just at the end like print alphas, print betas, tuple instances must be integers or slices, not strings. Hmm? What was that again? Oh, so it's like, so is it like, do I need to get print? If I do these, I'm just printing the alphas. If I just do these, I'm just printing that, and so I just want these, which is basically hopefully the values. That's what I'm expecting. So I want these to be that, and I want these to be that, essentially. Just rerun it, maybe. Yeah, okay, cool. I have these now. Well, yeah, that's the, okay, cool. So I have these. So if I say print alphas, for example, 45 and betas 45, what do I get? What? Why? Hmm. Am I grabbing the wrong thing? Oh, what am I doing? Print. How do I access tuples in Python? That's a shame. Oh, beta. Python tuples is just the, yeah, just like these. Okay, cool. So if I just yeah. Oh, I know what the problem is. This is betas. Cool. There you go. So is this running or? Yeah. Cool. So now I have the alphas and the betas, and now I also have the expectation values, right? And so what I want to do is I want to 3D plot, 3D scatter plot. MATLAB. No, MATLAB. Matplotlib. 3D scatter plot. Cool. Or just, yeah, I guess so. That's going to be complicated. Just, okay, just like scatter, just like that. Scatter, and so it's going to be basically alphas, betas, e-values. E-values. Okay, but there's a pattern in here. What is these? No, what's wrong? Invalid value, what? What? Let's just not touch the fix size for now. Marker M. Rand range, rand range. Okay, so I have no idea why is this not really. So what is the print alphas? So length. I want a 3D plot. Why is not like are those sizes correct? They all should be the same, right? Yeah, but why is it not printing in 3D? Access 3D. I actually have to. Where is this even used? I mean, it's not even used. Oh, register 3D projection. Maybe I just have to import that. Hmm. Mm. But you can see there's a wavy pattern in there as well, right? So that applies as well in this case. And what if I just like have, for example, I still want to see the 3D though. Matplotlib 3D. Range. Okay, so that plot. Mesh grid, make data. Plot the surface. What about I just try this in another cell? So I do these and I say, well, x, y, and z are like alphas, betas, and e values. So this is just, you know, these, right? Two-dimensional. Why? Why does z need to be two-dimensional? I don't get it. Customize. I don't want to customize these. Let's just do like these. Why? Why does this need to be two-dimensional? I don't get it. Okay. So it just says it expects it like, okay, so that's what should do the trick. Oh, there you go. Cool. So we don't want this to shrink. No color bar. No, we want the size a bit bigger. We don't care about the temperature. That's just like, I think it's that's where this two-dimensionality was No, I don't know. I don't know what's that, but like you see that like shape in there. And now what if we basically say you know this adds it to just to one qubit, right? And this adds it to uh, like or better. So this just like yields a like the to the 0 0, and this just yields to the 0 1, for example, right? So now you have unexpected indent where, oh yeah, sorry, Python. So it does these. So we're just having like a y and a z here. Oh yeah, but that z is not good. No, that z is not going to do anything. We let this be like an x. Okay, what it actually does. So yeah, but it's still the same shape. It's interesting for both parameters. And if we just mess around with these and now like we add a Hadamard gate and just a Hadamard gate, let's see what happens. What? Really? No, let's just add like one Hadamard gate to QB1. Really? You still get that nice thing? Something must be off here. I think something's wrong. I mean, the circuit is pretty well. What if the Hadamard like is applied on? What if we add a control X after the Hadamard, or just not after the Hadamard, like in general? Or control Z. I don't know why doesn't these change the expectation value? That's really confusing. I might be doing something wrong. Anyway, that's something that I'll definitely be exploring farther. As you can see, it's definitely something interesting to play with. I must be doing something wrong in here in terms of expectation values, because I would expect to see something pretty messy. As I was seeing with just like playing with one qubit and something not parameterized. I mean, okay, let's do the following. What if I add a third qubit? But and now I basically you know do like, so these would be the Kronecker product of these, and so we get the eigenvalues, and it's 1 minus 1 is 1, okay. So what if I just do like, this is, oh, basically what I can actually do is I can just multiply, can I not just multiply R by these? Probably. So 1, then 2 minus 1 is 1, 1, okay. Can I not just say like R times so eigenvalues being these, and then eigenvals. So I cannot just say eigenvalues. I think what we want is a dot product, so think that's what we probably want. Counter or float. Dot product. Now by dot product. Just dot AB. Now by dot. It's word operand. Oh. You mean that it should just do like this? No, but that should be. What's dot product? The dot product, it's basically, yeah, that's just the sum of a, yeah, it's basically these, right? So why I cannot just divide this by 100? Hmm. But that actually, so eigenvalues. What is values? This is just the array, right? That would be like a number, right? Maybe it's just the fact that it's a float number. That's maybe what it doesn't like. Float two integers. So float array as type int. Okay, something like this. So there you go. And then so I should just do this. There you go. And so now I have eigenvalues. Divide by 100. Can I do this? No, I don't get it. Okay, whatever. I'll stop here because it's just too late. It's definitely too late. But yeah, you get the idea of what I'm trying to do. I'm trying to visualize this a bit more, the expectation values in 3D and stuff like that. And I'm just a noob with all these. But I just want to get a sense of, you know, why it makes sense or not. And I think probably you'll just try to finish that in the next video and then dive into the actual paper that I actually lost already somewhere in here. Cool, yeah. But that's basically the observable that we're trying to actually calculate the expectation value from. So, is this the right way to do it though? Yeah, I think so. It's the right way to do it, right? Like I don't have to change the measurement basis or anything. I think that's the right way to do it. I hope so. I mean, at least I'm getting some results that kind of seem to make sense. But now this was not changing, so I don't know. Just wanted to kind of create more complicated circuit structures so I could see if that somewhat like is preserved in here. Anyway, cool, long video.